Okay, so what your course coordinators have asked me to cover is Laplace transform, and that is a mathematical topic which we will be using, well, I guess you will be using all the way till retirement, because every time you have a system with a response function, this is how it's analyzed. And every time you have a differential equation, if you're looking to solve it analytically, that is how it is solved, at least in a lot of the engineering applications. We will not go very deeply into whys and wherefores from the mathematical point of view. We don't have the time. What I will do is I will simply introduce you that transform, and I will prove a few of its properties, and then I will put it to good use as a way of solving differential equations and analyzing response properties of your system. Okay, so item 1 on the agenda, Laplace transform. If we have a function of time and the function is causal, so we have f of t such that f for times that are less than 0 is 0, so our time begins to tick at time 0. Then the Laplace transform of it, denoted L of f of t. Another notation is f of s, is the following integral. From 0 to infinity, your f of t e minus ts dt. So far, so obscure, it is not clear why we would want to make a transformation like that, but as you will see by the end of this lecture, this integral has a lot of useful properties. And we will first cover the various elementary properties of it, and then we will see how it simplifies a lot of things in the sort of engineering mathematics that you are going to encounter. So, properties. Just like any integral, Laplace transform is linear. That is, if you put into it a linear combination of functions, out comes an identical linear combination of Laplace transforms. So if we put L and apply it to alpha f of x plus beta g of x, where f and g individually have Laplace transforms, of course you know that we can split up integrals of sums into sums of integrals. We can take scalar multipliers out of the integrals, so what is going to happen is we will have alpha times the Laplace transform of f of t. This shouldn't be x, this should be time, and then plus beta, the Laplace transform of g of t. In other words, linearity. That is the simple property that doesn't actually require all that much of a proof. A slightly less obvious thing is the time shift property. If we take the Laplace transform of a signal that has been shifted in time by a quantity t naught, well, this time we will have to do a little bit of sweating. So from the definition, 0 to infinity, f of t minus t naught, then the same e minus ts, and then dt. In order to reduce it to the same form as here, we need to have the same time argument. We need to have it here, here, and here. So what I'll do is I will multiply and divide by the exponential of t naught s. What that is going to do is it will modify my index for the time to match the argument here of this function. So we have an integral, and I will not yet write the limits because the limits will also be modified. Yes?
So is there a seeds code?
I don't think that system ever worked, and so I stopped using it. There is an analog, sustainable, dolphin-friendly sign-in sheet, which you can use. We do it much like that thing, the ancient Greek way. Okay, so we will have f of t minus t naught, then e plus t naught s, then t minus t naught s. So remember, multiply and divide. E minus then ts dt. What I'll do here is I will put that and that together so that I have this argument, and I will take that out of the integral, which I can do because my integration variable t, and here I have a constant number t naught. Okay, so what happens then is I have e minus t naught s integral from, so far I think it's still from 0 to infinity, then e minus, and then we have t minus t naught s, f of t minus t naught, but still dt. And in order to have it all uniform, what I'll do is I'll have dt minus t naught. Of course, the differential of a constant is 0, and so now we have everything uniformly shifted. And the final thing, of course, is to shift the integration variable. So what I'll do is I'll introduce tau equals t minus t naught, and then we will have to decide the limits. So we have an integral, then f of tau e minus tau s d tau, and when t was 0, tau would be minus t naught, and when t is infinity, if t naught is finite, then this is still infinity. But remember the original property that we had for our function. At negative times it had been 0, so this integral actually remains an integral from 0, so minus t naught s, not forgetting that in front. So e minus t naught s integral from 0 to infinity f of tau e minus tau s d tau. And that, of course, is the original Laplace transform, and that proves our time shift property, e minus t naught s L of f of t. So if we shift our input by a certain amount, the output gets multiplied by this exponential. So that is the time shift property. Those of you who deal with digital signal processing eventually will see a similar list of properties for Fourier transform, but here we have to deal with the Laplace transform because this is an engineering module. Okay, so that is our property A. That is our property B. So the next one, C, is, I think, time scaling. So if we scale our time, if we go L, f of alpha t, we make time go faster or slower. Once again, you plug it into the integral. It's going to be a little bit easier because, of course, 0 times alpha is still 0, so you wouldn't have any alteration of the limits. I will leave that as the homework exercise, dragging that shifted scaled time through the definition, and I will just write out the answer here. It will be 1 over alpha L and f of t. Right? And if we use the notation that we have, probably we should actually use the f of s notation. So the image also gets scaled in the argument. So we have f of s that is divided by alpha. All right, so this operator notation is less convenient in this case. Okay, the next property, and the important one, which we will be using a lot today, is differentiation. what is the Laplace transform of a derivative. And this is one of the killer applications of this, as you will see now. When we take the Laplace transform of a derivative, it maps differentiation into multiplication. And it's a lot easier to multiply than it is to differentiate, and this is why ultimately this thing had caught on. So, Laplace transform of f prime of t. From the definition, so integral 0 to infinity f prime of t e minus ts dt. We integrate this by parts, so our u is e minus ts, du is minus, I think in this case we're differentiating with respect to t, so minus s e minus ts dt, and dv is f prime of t dt, and v is therefore f of t. Plugging it into the expression for the integration by parts, remember uv from 0 to infinity minus integral 0 to infinity v du. So u and v, we have f of t e minus ts from 0 to infinity, then minus and another minus over there, plus s integral 0 to infinity v du, so f of t, and then e minus ts dt. And notice what we have here. Let's take a good look. At the infinite limit, we assume that our input has decayed. Right? Most engineering inputs, whatever it is you're doing, is probably going to be dead at infinity. Philosophical assumption, so to speak. So at the upper limit, we have a 0. At the lower limit, however, the exponential becomes 1, and the initial condition we might have that is non-trivial, so f of 0. So what we have here is minus the original value, so the initial value, plus s, and that's the Laplace transform, so s f of s. And this is very important. Notice what happened. The original function has a derivative. Its image after a Laplace transform has simply been multiplied by the argument. So what we can do is, faced with some horrendous differential equation, we can transform both parts. We will get algebraic equations, solve it for f of s, and then invert the Laplace transform, and that's our differential equation suddenly solved with not too much hassle, assuming we have a table of Laplace transforms handy. Okay, likewise for the integral equations, the proof is pretty much identical. You just do the integration by parts in reverse, but the Laplace transform of an indefinite integral, so 0 to t f of tau d tau, I will simply leave that as an exercise and write the final answer. This was multiplication. Predictably, integration is a division by the argument, and we have f of s. That's the transform. These are the basic properties, and you can already glimpse the fact that integral differential transformations in the Laplace transformed representation are going to be significantly easier. At least analytically. Numerically, that is a bit of a problem. Fourier transform is much better numerically than Laplace transform, but at least analytically, it might make our life ever so slightly easier. And for simple models, it's not actually that hard to do Laplace transforms. So item 2 on the agenda is examples. Let us transform a few things and see in general how that is done. So, a f of t is a constant. Well, we all know how to integrate. So L of f of t is going to be integral from 0 to infinity constant e minus ts dt. Constant comes out, and then 1 over s e minus ts from t equals 0 to t equals infinity, and not forgetting the minus in here. At the upper limit, clearly 0. At the lower limit, 1. The lower limit comes with a minus. That cancels that minus. C over S. So, not particularly complicated. Let's try something bigger. If we take, for example, f of t equals t, or powers of t, then we will have to sweat a little bit. You know, we need an integration by parts in there, but this is not complicated either. So f of t is t, then L of f of t, integral 0 to infinity t e minus ts dt. Integration by parts, u is t, du is dt, dv is e minus ts dt, v is minus 1 over s e minus ts. The rule for the integration by parts is you put into u whatever gets simpler under differentiation, and you put into v whatever it is that you don't mind integrating. And so this is how we did it. So let's continue here in the interest of saving space. So we have uv, so that is going to be t over s e minus ts from 0 to infinity. Then that minus cancels the minus that we have in the integration by parts. So plus integral 0 to infinity. And we have v du. So 1 over s e minus ts. And then du is dt. So that is something we can easily take. Let's take a look at the limits. This at infinity is 0 because of this exponential. At 0 it is 0 because of t, so we have no first term in there. And here another instance of s will pop out, so minus 1 over s squared. And then e minus ts with a minus, and then from 0 to infinity with respect to t. At infinity the exponential is 0, at 0 the exponential is 1, minus cancels the minus, 1 over s squared. And that is just for t. If you have t to the power n, you would have to do this integration by parts n times. Every time you would have extra factors popping out. I will not do that, that would be quite lengthy, but I will simply give you the answer that the Laplace transform of t to the power n is the following. It's n factorial over s to the power n plus 1. And as you can see, the special case of n equals 1 is right here. What this also means is Laplace transform has nice ways of representing pretty much any function you can throw at it, because even if your original function might have trouble getting itself integrated, its Taylor series will always be easily Laplace transformable. Right? Expand it in a Taylor series, run the transform, and you'll be fine. So that is again another hint that we are dealing with something that in the engineering practice is singularly useful. Then trivial things like exponentials. So c f of t is e. Let me match the notation here, at. Again, we would have to sweat a little bit, but that's a noble sweat. I think we should go through the process here somewhere. So L of e, and I've used at. That will be an integral from 0 to infinity, e to the at, e to the minus ts dt. Merge the exponentials. Take the t out of the bracket. So integral 0 to infinity, e minus, and then we will have s in here, and then minus a, and then t. So when we open the brackets again, minus minus gives us at, and then minus ts is here. So dt. Integrating that, minus 1 over s minus a. So that is the integral, and then e minus s minus a t from 0 to infinity. And once again, at the infinite limit, we assume that everything has decayed. At the 0 limit, that is equal to 1, and so we have 1 over s minus a for the exponential. And yeah, that is correct. Likewise, I will not go through the nitty-gritty for those functions, but you can do the sine and the cos. It's actually quite straightforward because we already know the Laplace transform of the exponential, and I would remind you that cos omega t is, according to Mr. Euler, is e minus I omega t plus e plus I omega t divided by 2. The famous Euler's formula in reverse. And so if we do know the Laplace transform of the exponential, we also know that Laplace transform is linear. We can apply it to each individual exponential here, put them together after a little bit of trivial mathematics. For a cos, we have s over s squared plus omega squared. And for the sine omega t, we have omega over s squared plus omega squared. And again, the detailed derivation of that is left as a homework exercise, or maybe it's actually in the problem set that we will do later today. All right, so enough preliminaries. Let us go directly to the useful part now, and that is solving ordinary differential equations. So 3, solving ODEs. And I will start with an example that, if you've been around and paying attention in your calculus classes, would strike fear into your eyes, because the equation is not uniform. And you know exactly what it means. So we have y prime of t plus y of t equals e to the minus t. To remind you what would have been involved were we to solve this the ordinary way. We would have to consider first the uniform version of that equation. We would have to substitute the trial function, the exponential here, find the index of the exponential, do the indeterminate coefficients, then declare them to be functions, resubstitute into the inhomogeneous version here, find what those functions are, get the integration constants out, substitute into the initial condition, find the integration constant, and at the end of a good 45 minutes of effort, we would have had our solution, the conventional way. Here, so let me also draw the initial condition. Let us use the Laplace transform and the properties that we have just demonstrated. Well, we know what the Laplace transform of a derivative is. We have worked it out here. Our initial condition is 0, so that thing isn't there. We just have s times f of s. So in this case, it will be s times y of s, the Laplace image of that, plus the Laplace image of this, y of s, equals the Laplace image of the exponential. And we know what that is. If we are transforming that, we will have a is minus 1 here, s minus minus 1, s plus 1. 1 over s plus 1. A fairly trivial algebraic equation. Let us solve this for y of s. So we would have y of s equals s plus 1 here, s plus 1 there, 1 over s plus 1 squared. And then the magic comes. You open a giant book that says Laplace transforms, and it has thousands of pre-calculated Laplace transforms. You find which one corresponds to that expression. So, book. Or you can just take various integrals until you find, or you can sometimes even guess it. What comes out is y of t is t e minus t, I think, in this case. Yeah. And if we check it by differentiation here, we will see that it satisfies our equation. And if we check the initial condition is satisfied. So, by using a clever integral transformation trick, in my time, 20 years ago, when I was an undergraduate, this would have been a book. In your time, it's Mathematica. You type inverse Laplace transform, plug that in, a millisecond later, you have this. As you can see, both rather neat, compatible furthermore with differential equations of higher order, as we'll see, compatible with all sorts of messy source terms that you will have to handle. If you've seen partial differentiation and partial differential equations by now, you will also appreciate that it would simplify those. So clearly, for all the effort we have put into deriving all of these properties, well, they seem to be rather handsomely paying off. Okay, so that is the first example. Let me do another one, this time the wave equation, second order. So this is example A. Example B is going to be f double prime of t equals minus omega squared f of t. You can probably guess, or in fact remember by now, that the solutions here are sines and cosines, so the equation like that by itself presents no particular complication, but the moment we have a source term in the wave equation, that turns into a serious nightmare, because this is a second order ODE. And of course, what we need to do is we need to extend that property we have somewhere there to the second derivative now. And this is something I also want to do on the board because it is quite instructive. In fact, this huge simplification property extends all the way to an arbitrary number of derivatives. So let's just do the second derivative quickly on the board. So we have a Laplace transform 0 to infinity f double prime of t e to the minus ts dt. Well, we'll just have to do it by parts twice. So we have our u equals e minus ts, du is minus s e minus ts dt. dv is f double prime of t dt, and v is therefore f prime. Okay. Plugging all of that in here somewhere, uv, so f prime of t e minus ts 0 to infinity. That minus cancels the minus from the integration by parts, so plus s integral 0 to infinity v du f prime, and then that, so f prime of t e minus ts dt. And you can see again, we assume that at infinity everything vanishes, and we are left with f prime at 0 with a minus. So this is the Laplace transform of f prime times s. So this is s Laplace transform of f prime of t, then minus f prime of 0. And we already know the formula for the Laplace transform of f prime. So this is going to be s, and then sfs, and then minus f of 0, and then minus f prime of 0. So let us take a look at what initial conditions we had here. And the initial conditions were f of 0 is 0 and f prime of 0 is 1. We plug them in. That is 0, that is s squared, f of s minus 1. And that, in our case, is the Laplace transform of the second derivative on the left-hand side of that equation. On the right-hand side, we of course simply have minus omega squared f of s. And therefore, we pretty much have solved it already in the Laplace domain. On the left-hand side is s squared f of s minus 1, and the right-hand side is minus omega squared f of s. As you can see, trivially easy to solve for f of s. Move that over there. Omega squared plus s squared f of s equals, move 1 over here, 1. Therefore, f of s is 1 over omega squared plus s squared. Remember what I told you about the Laplace transform in that case of a sine. So that is different from that by 1 over omega. So therefore, f. So this is 1 over omega times omega over omega squared plus s squared. That inverts into a sine that we just keep. So f of t is 1 over omega sine omega t. And that's it. You can literally confirm that that is something that satisfies both the initial condition and the differential equation itself. So this is, as you can see, rather useful for at least individual differential equations. Now let us become chemists. We are chemical engineers after all, and go and solve another problem, common problem. So reaction in the presence of the substance being added to the system, where the source term of the differential equation would create us trouble if we were to solve it by conventional means, but we would have rather less trouble if we solve it using the Laplace transform. Okay. We have an input. Just me standing there with a shovel and adding substance at the rate Q to a reaction A into B, K plus, K minus, and we would like to solve the corresponding system of kinetic differential equations. So dA by dt, as you know perfectly well, A is depleted by the forward process, so minus K plus A. It is replenished by the backward process, plus K minus B, and it is replenished at a constant rate by the input, so plus Q. Then dB by dt is replenished in the forward reaction by A, K plus A, drained in the backward reaction, so minus K minus B, and this is our system of equations. Again, if you remember how to solve systems of ordinary differential equations, you will remember a considerable amount of effort made worse by the fact that we have a non-uniformity there in the shape of this source term. However, as you can probably see directly, the Laplace transform of this is trivially easy. We know what the Laplace transform of the derivative is. We know the initial condition. We are told that the reactor was empty at the beginning, and so we can almost Laplace transform this visually. Right, so the derivative of A gets transformed into SA of S equals minus K plus A of S plus K minus B of S. So I'm just using the S argument as an indication that this is in the Laplace domain. The Laplace transform of a constant I gave you at the very beginning, 1 over S, somewhere there. So that is going to be plus Q over S. Then SBS, that's the derivative, is K plus A of S plus, or rather minus, K minus B of S. And that is actually a system of algebraic equations. Nice and easy to solve. Well, you've all been to the kindergarten. You know how to solve systems of linear algebraic equations, so I will not bore you with the process of pulling A of S and B of S out of this. I will simply just proceed with the result. I think you have the long story in your handout, but after we've done that, what we get is A of S is Q over S times K plus S over K total, and I will define that in a moment. K total is K plus K minus. And this will take some looking at. You can see it is not obvious what the inverse Laplace transform of this function might be. And likewise, after we work out the B, we will get K plus over K minus plus S times A of S. Okay, so we solved the problem in the Laplace domain, but notice we have, power 2 in the denominator. We have S in the numerator, but we do know, firstly, that solutions of such systems of differential equations are always linear combinations of exponentials and occasionally polynomials if we have non-uniformity, so we expect exponentials and polynomials in the answer. And secondly, we do know that once we have elementary fractions like this, so 1 over something, or squares in the denominators, we know how to invert the Laplace transform. So let us break up this A of S into partial fractions. And again, you had it all in your mathematics A levels at school. How do you break this up into individual fractions? So I will not bore you with the process. I will simply write the answer out. We have A of S, and that is Q K minus over KTS squared plus Q K minus over KT squared S minus K plus over KT squared KT plus S. And you can just check by direct inspections, and if you put this fraction back together, it is equal to this. What do we see here? Well, we'll see 1 over S squared, and we know exactly what that corresponds to. There it is. It corresponds to T. We have 1 over S, and we know that that corresponds to a constant. We have a bunch of constants, but ultimately something plus S, and we know that that corresponds to an exponential. And so, after we do the procedure, the reverse matching, not losing any coefficients, in the process Q K minus over KT times time plus Q K minus over K squared T, that's our constant, and minus K plus over KT squared E minus KT over T times T. A few things to note. So this is A of T. Notice the usual exponential term that pertains to the chemical reaction, but it slowly decays into nothing as time proceeds. It gets subtracted out of this constant. Notice the asymptotic term that grows linearly with time, so the total quantity of the product is asymptotically linear. This is because we are adding this amount per unit time, so ultimately it will grow with that. And so that's A. It would have been a lot harder to do B because you add an extra fraction term that would have multiplied here. Thankfully, we have conservation of matter for B. So we know that there's A of T plus B of T. If we add these two derivatives together, that will cancel, we'll just be left with Q. And so this sum is equal to QT. And if we know A, we can easily work out B of T from there. Okay, so I think that's as much as I want to torture you with before we hit the problem set. There is this lovely integral transformation called Laplace transform, which all of you should be able to do because all of you hopefully remember how to integrate. Turns out that it maps derivatives and differentiation operation in general in the time domain into multiplication in what's called the Laplace domain. And that reverse transformation is not too hard to do. And therefore it is very useful for solving, as you can see already, 3 classes of differential equations. We've done something perhaps from physics with a source in it. We've done the wave equation and we've done the chemical kinetics equation. For a fairly complicated system with an input, all within, the 20 minutes that I've been scribbling on this board. This would have been a much longer story if we had to do it the conventional way in the time domain. So this is what it is, this is what it's useful for. I have not done any mathematical technicalities for when it exists, when it converges and so on. We don't have the time in this course. We're engineers, we're just here to use it. All right, any questions?